Hi everyone, thank you very much for attending the conference. My name is Rustem, I'm machine learning engineer at Instrumental, and today I want to tell you about how to build scalable end-to-end deep learning pipelines in the cloud. First, I want to start with takeaways from the presentation. First of all is that cloud-native orchestrators are very convenient for constructing scalable end-to-end deep learning pipelines, that you can use a lot of different services and it will depend on your context. And it's very easy to deploy this sort of workflows, even for research projects. So first, let's take a look at how the usual data science process looks like. First, we start with business understanding, where we try to define objectives, find metrics, and also identify data which we can use. Then the next step is data acquisition, where we find and clean the data. Next, we build the model and train it, select the features which we can use from the data, and so on. Once the model is prepared, now we can deploy it and finally get feedback from the customer. But actually, last three steps is a very iterative process. And we want to be able to start fast, be very flexible in case we need to change data or infrastructure, and be able to integrate with existing production infrastructure. So now let's switch to how Serverless can help us with that. And first, let's take a look at what are the different ways to deploy applications. So here you can see the spectrum of different ways to deploy applications, from on-premise, where we control the whole stack, to, for example, functions as a service, where we only control the code, or containers as a server, where we control everything above container level. So in my case, I will cover as a serverless three main columns of this spectrum, from containers as a service to function as a service. So on very high level, we can describe serverless as on-demand cluster, worker, or service, which will scale based on your consumption. There are no upfront costs, pay-as-you-go pricing, and no payment for idle time. Small asterisk here, which I will describe later. Also, there is low operational support. The whole infrastructure can be defined as infrastructure as code, and there are built-in service integrations with other AWS services or external services. So how serverless would help us in our case? Because there is low operational support and no upfront costs, it's very easy to start. Because we can define our infrastructure as code and there are built-in service integrations, the infrastructure is flexible. And because it's also scalable, we can integrate it with our production infrastructure. When designing a deep learning pipeline, we need to design three main steps. It's data preprocessing, model training, and model inference. With data preprocessing, the main task is to get data from multiple sources, and the main challenges are combination of different languages or frameworks, and scaling based on data. With training, our main tasks are train and publish the model, probably check it against multiple sets of hyperparameters to find the best architecture, and handle semi-automatic logic because part of the training is automatic, but also we don't want to push model into production which doesn't work. So the challenges here is that GPU instances are pretty expensive, and there is a high level of uncertainty compared to normal software engineering. And finally, model inference or predictions, where we just want to make predictions. The main challenge here is that we have to adhere to production requirements, aka latency, load, and cost, and we may need to handle multiple frameworks or model versioning. So first I want to start with describing container as a service and function as a service. So here I would use the term serverless cluster. In our case, it's a cluster or worker which will scale based on your consumption, where it's just required to define code and launching configuration without handling the cluster itself. There could be different scaling techniques though. It could scale based on job queue, like with AWS Batch. It could start one VM per job, like with Fargate or SageMaker, and it can start worker per one job, like with AWS Lambda. So with AWS Batch, we can just consider it as a cluster, which will scale based on job queue, but at the same time, we only need to define a computational environment and scheduler, but everything else is defined for us. So we don't have to handle cluster itself. Next is AWS Fargate, which is basically container as a service which starts 1 VM per job, and it can be used for both on-demand processing, which we'll be using in our case, and as a scalable web server. And keep in mind that Fargate can only use customizable CPU instances, so it cannot use standard EC2 instance types. With SageMaker, there are different types of jobs we can use. First is processing jobs, which is basically CAS service which starts VM per job. It's limited to specific ML instance types, but at the same time it can mount S3 buckets as disks. And training jobs, which basically has more features, but it also only can be used with specific ML.instance types. But at the same time, it handles monitoring, hyperparameters, data import, and model export for you. And comparing to processing jobs, it has support for spot instances and handles checkpointing for your model. So if we put all of these services together, we can see that AWS Lambda, which is function as a service, has the fastest startup time, around 100 milliseconds, best pricing per 1 millisecond. It's very scalable, so we can start 10,000 lambdas at the same time. But at the same time, it's very expensive per CPU per second, and there are multiple limits with it. So usually it's best used for short-term processes, but which we need to start in parallel. On the other hand, we have AWS Batch, which is basically a cluster which scales based on the number of jobs. It has slow startup time compared to other services, and it has pricing per 1 second with a minimum of 1 minute. And it's best to use for combining CPU, GPU, medium running task processes. And in the center we have SageMaker and Fargate, which are basically pure container as a service, and where Fargate is best suited for CPU long running processes and SageMaker is best suited for GPU long running processes. So next, let's compare CPU and GPU for machine learning applications. Usually, we use GPU for training deep learning models, but for example, if we look at the inference, there are multiple axes of comparison, not just speed. We also want to be able to compare them based on cost, because it's important, and also scalability. So here is the table, which has different times and costs per inference for Inception v3 image classification model, for different instance types, and AWS Lambda. In short, you can see that AWS Lambda is the slowest here. And also, it's almost the most expensive per 1 million of predictions. But at the same time, if we compare Lambda to other instance types, we don't have to pay for idle time. So, for example, for the whole month of having any of the service on this table, we can see that we will have to pay for idle time anyway. So in this example, if you have less than 1 million invocations per month, then Lambda would be the most cost-effective way to run predictions. Next, let's look at how different services are different in terms of pricing for the same compute. So here we can compare AWS Lambda, Fargate, and Batch for almost the same configuration. As we can see, Lambda is the most expensive option here, but at the same time, keep in mind At first, first of all, the pricing here is per 1 millisecond compared per 1 second for Fargate and batch, and where there is no minimal time for AWS Lambda. With Fargate and batch, the minimum is 1 minute. So if your job takes 30 seconds, then it's better to use AWS Lambda. And if we compare Fargate and batch, with Fargate we can be almost sure that we don't have any idle time because it's 1 VM per job. And with batch, although it's very cost efficient per hour, we may have some idle time, so we have to keep it in mind. And next is GPU. Let's do the same comparison for SageMaker and batch. So for SageMaker, we can see that it's more expensive compared to the same configuration of batch, but it also has zero idle time, and also it has a lot of additional features which will help you to handle your training better. So now let's take a step back and look at basically how we can define an application based on what we learned. In short, let's say we want to put our application just on one machine, but our whole application actually consists of different steps, and steps may have different requirements. And for example, only modular training may need GPU. So actually we can just divide the steps on to use different services. For example, for data gathering we can use FAS because we have multiple data sources. For data preprocessing we can use multi-core CPU, and for model training we can use GPU. In this case, we try to optimize for GPU idle time. So to organize this sort of application, we need to be able to connect different services together. So now let's take a look how we can do it. So basically here I want to specifically look into cloud native orchestrators, although there are also ways to connect services together like REST API requests, but it's best for synchronous services for which don't take a lot of time to process something, and queues, but which are best for asynchronous services, but it may take a lot of time. It may be harder to troubleshoot your application and have complex logic. So cloud native orchestrators is the best for our sort of workflows, where we would need to combine different services together because it has native support for them. It has central monitoring, so it's easier to troubleshoot your application. And with logging and tracing, you can actually construct very complex logic. And it scales on demand. So there are multiple services available to you if you want to construct this kind of workflow. First is Amazon Step Functions, which is basically a graph-based workflow where you can define each node as a different service. And it's very flexible in terms of services which you can use, from Fargate, ECS, SageMaker, Lambda to Glue and EMR. So it has provides a way to implement even very complex logic. So for example, you can do a custom error handling, or you can process some tasks in parallel. Also, you can do loops and scheduler. The pricing with step functions is pay as you go, so you pay for state transitions. Next are SageMaker Pipelines. It's a DAG-based workflow. It's a little bit more limited in terms of processing nodes. It can only use SageMaker, processing, training, Databrew, and Lambda. But it can have some complex logic, and you can make a complex step like human review step. And it's free, but in a way that basically because you pay for the compute like SageMaker processing or training. And finally, managed Apache Airflow, which is a DAG-based workflow. and it's very flexible in terms of what you can use for processing nodes. Basically, anything Airflow can, it can use anything which Airflow can support with different plugins. It has very high flexibility and you can run it locally, but the problem is that it doesn't scale automatically, so you would need to adjust your instance type. And here you don't have like pure pay-as-you-go system, you pay instance time. So if we put all of them together, we can see that basically Airflow provides the best flexibility, though it doesn't have the full serverless experience. SageMaker Pipelines is very focused on machine learning workflows, but it has more limitations in terms of services it can integrate with. And AWS Step Functions have integrations with with a lot of AWS services, and it has pay-as-you-go system. There are multiple cons though, because it cannot run in local environment, and we have to handle pipeline as artifact. So in our case, we will use AWS Step Functions because it provides integrations with all different services which I mentioned before. But SageMaker Pipelines can be useful as well in case you want to start with research and then transition your pipeline into production. So let's summarize our approach so far. So our current plan is that we will use AWS Lambda for short and parallel processing. We will use scalable container service AWS Batch for heavy and parallel processing and GPU training jobs. We will use SageMaker for our training jobs and distributed training. And we will use Fargate for long-running processing. And finally, we will use Step Functions to organize all of these services together in one workflow. Let's start with data preprocessing. As you remember, here we need to get data from different sources and transform it. So first pattern which we can use is to basically use SageMaker processing jobs for heavy processing and then parallelize some tasks using AWS Lambda. In our case, it's helpful if we want to make a combination of parallel processing and heavy processing. And with SageMaker processing job, it may be easier to develop because we can mount S3 bucket as disk. Alternatively, we can use batch or Fargate for processing. The main difference here would be that we would need to pass data through S3 to batch and Fargate because S3 is not mounted. So how do you know if this would work for you? So if you have peak loads and you want to scale automatically, or if you have some custom logic like scheduler or error handling, or if you want to have a more customizable pipeline and you want to combine multiple frameworks or languages, where it wouldn't work. So if data processing should be synchronous, in this case calling AWS Lambda cluster would be easier because step functions are asynchronous. And if you have low CPU RAM consuming workflow and want to optimize costs. In this case, SQS or Kinesis plus AWS Lambda would be a cheaper solution. So here you can see the link to the repository, which has different serverless configuration files, which you can use to deploy patterns which I mentioned, specifically step functions, Lambda, with batch and Fargate. Next is model training. With model training, we need to train and publish the model and maybe check multiple sets of hyperparameters and be able to handle semi-automatic logic. The challenge here is high cost of GPU instances and high uncertainty of the pipeline. So first is pattern is to use SageMaker. In our case, we will use Mapper to prepare our training parameters, and SageMaker will handle the training itself. So the main advantage here is that SageMaker will handle a lot of things automatically. For example, it will handle hyperparameters and metrics. It will handle input model and input data and saving model in model registry and hyperparameter optimizations. And in case you're using SageMaker with spot instances, it will implement logic for checkpointing. And it can also handle distributed training if you need it. Alternatively, you can use AWS Batch. The main difference here would be that instead of having all the features which I mentioned automatically, you would need to re-implement them manually. But at the same time, you can have more flexibility in terms of logic you have within the service and starting AWS Batch. And also you have to keep in mind that with AWS Batch you will have more idle time and you cannot run distributed training because you will have one job per instance. And finally, you can actually use step functions with your external GPU. It could be either integrating production cloud environment with on-premise infrastructure or with some external services for GPU training. So in this particular case, you will use your step functions to prepare data and share it to your external GPU. And external GPU will make requests to step functions and will check if there are new tasks available. If the new task is available, it will download the data, train the model, upload model to S3, and then it will report to step functions that task is completed. So how do you know if this would work for you? So if you have peak loads and you want to scale automatically, then it would work perfectly. Also, if you need to run training jobs occasionally and want to minimize idle time, then it would help you because you don't have to maintain the full cluster. If you have some custom logic, for example, scheduler or error handling, it could be, for example, post-training tests or pre-training tests as well. Or you want to integrate external infrastructure or multiple AWS services. So where it wouldn't work? If you have a very short model training, which can be run synchronously, then in this case cluster would be easier because the functions don't support synchronous workflows, except for express step functions, but they have a lot less integrations. And if you need to maximize training speed. In this case, using cluster minimizes startup time because with both AWS Batch and Amazon SageMaker, there is some time for starting the job on the cluster or worker or VM. So here you can see the link to the similar repository where it has configurations files which will deploy step functions together with Lambda, Batch, and Amazon SageMaker, just within the patterns which I mentioned before. And finally, model predictions. Here we want to make predictions based on new data, and we want to be able to adhere to requirements like latency, load, and cost, and be able to handle multiple frameworks and multiple models in production. So here we can see how the usual architecture for inference would look like if we want to implement something like deep learning API. So here we would have route 53 for DNS, load balancing ILB for serving requests to different VMs, ECS for handling our instances, and auto-scaling group in case we want to scale our cluster, and ECR for storing our Docker image. So as you can see, it can be pretty complex. If we want to use AWS Lambda, the architecture will be a lot easier. So we just need to deploy Lambda with our model, and we can just use API gateway. Alternatively, we can connect Lambda to SQS in case we want to use it for batch predictions. And finally, we can actually connect it to step functions in case we want to have some more custom logic. If we're using step functions, we can actually use it for different custom logic implementations. It could either be A/B testing, where, for example, we want to roll out a new model slowly and make sure that our new model performs better than the old one, or we can use multi-armed bandit logic. Also, it could be used as a scalable inference, where we want to batch our predictions together, or if we want to use different modules and different frameworks. So how would we need to import the models? So here there are two ways how we do it. If we're using Lambda package for our code, then in case we have lightweight framework like Onyx or TF Lite, then we can keep model together with our code. If we're using frameworks like Keras, TensorFlow, or PyTorch, then we would need to import it from S3. So alternatively, we can use Docker. With Docker, the limitation is 10 GB instead of 250 MB for Lambda package if we use zip. And in this case, we can keep model together with Docker image. The challenge here is that loading the model from Docker can take more time compared to zip package. And in case your model is small, it doesn't make a lot of difference. But if you have large model, but still less than like 200 MB, and you want to optimize your cold start, then in this case, using something like TF Lite or Onyx would be the best way to have the fastest prediction during cold start. So now let's compare different inferences based on different frameworks. So here you can see three frameworks which are used for making predictions on the same Inception v3 model for image classification with two configurations, 3.5 GB RAM and 1.7 GB RAM on AWS Lambda. And here you can see two times: init time, which takes to import all the libraries and load the model itself, and inference time, which is basically the time it takes to make a prediction for one image. So here you can see cold cost and warm cost. Cold cost is inference time plus init time, and warm cost is just inference time. The main takeaway here is that, like, first of all, different frameworks have different init time and inference time. And depending on your needs, you may want to optimize for one or another. If you have batch processing and you know for sure that you will be processing a lot of jobs, then inference time, optimizing for inference time is the best. And in this case, it would be using Onyx. If, for example, you want to use it more as API, like a deep learning API, and you want to minimize your cold start, in this case, using something like TensorFlow would be more helpful, even though inference time itself is not very good. Also keep in mind that you can optimize your model specifically for the inference. So there are multiple life hacks if you want to use serverless inference. So first of all is the main one. You want to store your model in memory for warm invocations, so you don't reload the model. Second one is that you can use EFS for storing the model if it doesn't fit your package. You can store the model as part of the libraries, or and when you load it from storage like S3, you can actually download it in parallel if you have multiple vCPUs. If you have multiple CPUs, you can actually batch the workload and run predictions in parallel. And keep in mind that you can optimize RAM and timeout to optimize your costs. And you have to make a decision whether you want to optimize costs or speed. So how do you know if this would work for you? So if you want to deploy your model for pet project, then it would be great because it's very easy to start and architecture is very simple. If you want to make a simple MVP for a startup or project, then it would work as well because basically it will scale based on your needs and architecture will be flexible enough to make any changes. If you have simple model, then this architecture will reduce cost. Because it has zero idle time, it can adjust to your load and it may reduce your costs. And finally, if you have peak loads and it's hard to manage clusters. In this case, it would help you because Lambda can scale very well and it can handle 10,000 parallel requests without any problems. So where it wouldn't work though. So if you have to have real-time response, then it's better to use cluster. If you have to use a lot of data or you need to use a lot of processing power, then it's best to use a cluster. And if you have extremely large number of requests, based on the table we saw before, for example, with more than 10 million, 20 million requests, then cluster may be more suitable. So here you can see links to two repositories. They have prepared packages for AWS Lambda and Google Cloud Functions, including different machine learning and deep learning libraries. And feel free to use it for your projects. It has MIT license, so feel free to check it out. So to summarize, here we covered that we can use cloud native orchestrators for constructing this kind of end-to-end pipelines for training deep learning models. Second is that there are different services for both pipelines and compute, which you can use for your pipeline deep learning workflow. And it depends on your context, which services do you want to use. Do you want to optimize for flexibility, cost, speed, and so on. And finally, it's actually pretty easy to start with this kind of workflows, even for research projects. So thank you for your time. And actually, let me show a demo of this deep learning pipeline which I mentioned. So here you can see the command line where I have deployed pattern from my repository. So I will show repository like a bit later, but here I just want to show you that you just need to set up environmental variables, deploy application from the folder, and it will deploy the whole infrastructure which you need, like step functions, AWS batch, and AWS Lambda. So as you can see, it returned endpoint which we can use to call and start these step function jobs. Now let's take a look at how repository looks like. Here you can see the repository which I mentioned with different patterns. In my case, and you can see like they have a description of different patterns and steps how you can deploy them. In our case, we deploy deep learning inference pattern. Deep learning training pattern, and it consists of the 3 files. So it has serverless config file, which has all the infrastructure which we want to deploy, index.py file, which has Python code for AWS Lambdas, and it has requirements file for node modules. So here now I want to show you how the configuration file looks like. So here we define step functions, which I mentioned, where we can define any sort of step or service. And here are the main three parameters which you can use and you need to define is S3 bucket, which will be used for hyperparameters and models, compute type, EC2 or spot, or image name. So as you can see, it's very easy to provide parameters to this configuration file, and you don't need to there are some parameters mentioned here which basically deploy all the services like AWS Batch and all needed dependencies, but it will work very straightforward. Also here you can see the example Docker training GPU file, which contains a Docker file itself and sample of training model based on NIST. So now let's take a look at step functions and what we have deployed. So here you can see that we have 5 jobs which we just created from the endpoint. If we look at the job, we can see how the workflow looks like, and that it finished 2 steps successfully, and currently it's within the batch step. Also you can see the timings, and you can easily go to the CloudWatch logs of each individual step. So let's take a look at the batch step. So what it does is that it actually, and as you can see, deploys batch instances and runs jobs on top of them. If we go to the batch service itself, we will be able to see status of each individual job. So for example, here, we can go to job queue, and we can see the compute environment which was created based on the jobs which we have in queue. And here we can see all the training jobs which were created and what is their status. Finally, I want to cover the log part. One of the main pluses of using AWS Batch is that logging is handled for you. So for example, we can see the log stream for each individual job. For example, for this step. And for within the training step, we can see how the code is executed. And we can see the results. Okay, it may take some time to complete, but as you can see, one of our jobs is completed successfully. And now we can even examine each step and see what was the input and what was the output. So as you can see, it's very easy to deploy. So thank you again for your time. Here are the links to all repositories which I mentioned, and also a link to Inference benchmarks repository, which contains packages for all the benchmarks which I mentioned throughout my presentation, as well as link to my website where you can find all these repositories and links to other projects and courses. And feel free to shoot me an email if you have any questions. And also would be happy to answer any questions which you have. Thank you.